Or we can start. So, should I give some background or you will the background?
So I was thinking I will, but if you want to.
No, I don't want to. Just I
So hello everyone, I'm Nadia and I welcome you all to the very first event of Teach and Learn. Firstly, I would like to thank my RS Forum members, Rituraj, Suman sir and Mayuri Bora for their efforts in putting this all together, and of course thanks to our faculty advisors, Professor Somam and Professor Saurabh. So those who don't know, let me give you a quick idea of what this drill is all about. So basically, it's going to be an event of lectures every, let's say 2 or 3 months, wherein the scholars come and share their skills with other scholars, and in the process, the audience and the presenting ones all will be learning. So this is going to be the first event, and I'll present, and after me, Tajul will also present. It has come upon me to be the first one to present the first lecture, and the theme that I have chosen is, the slide share. The theme that I have chosen is physics of your problem. The reason for choosing this theme is that not many in our department are working on this topic, and not many know about this topic. So this topic is basically a tool that I'll discuss with you, and maybe some, if you're interested, you can go ahead and incorporate this tool into your research in some form, so that you can increase the dimension, add some other dimension to your research. So I'll try to make it simple so that everyone understands, and most importantly, it becomes interesting and no one gets bored. I'll try my best. So with this, I'd like to start. The title of my talk today is Physics Behind Modeling of Large Deformation Problems Using Smooth Particle Hydrodynamics. I've broken my presentation into small steps, starting with what physics of any problem means, so that you know what to expect in the upcoming slides. Secondly, what are the real-world large deformation problems around us, and what are the numerical modeling approaches that are in practice? And finally, what is smooth particle hydrodynamics? Starting with the basics, what is the physics of any problem? So basically, if we want to know the how of how anything works, anything in the universe, how it works, that would pretty much explain the physics of that problem. Let's take an example of something that we all experience every moment, every second, which is gravity. If we try to explain how gravity works using some fundamental rules and mathematics, obviously there will be some idealization, and if we are able to express it using some mathematical formulations and give a precise explanation to it, that would pretty much explain what is the physics behind gravity. Similarly, in this talk today, I will try to explain what SPH is, and most importantly, how it works, and what are its real-life applications and what's the scope. Before going on, let me take you through some of the real-life problems that we experience around us. One includes mass movements like landslides, debris flows, tsunamis, avalanches, mud avalanches, snow avalanches, etc. Other large deformation problems include fractures. Those doing their research in the area of structural analysis, they might know that when you're using tools like, let's say, finite element method, you will be able to predict when the structure will fail, where it will fail, but you won't be able to predict how the fracture will progress, how the failure plane will progress. So this is another large deformation problem. This is a beam column joint, and here it is a concrete gravity dam. Others include impact on structures. So we have dam break flow problems, we have debris flows when the impact on structures. This is another problem. Then there are collision of bodies, elastic collisions, inelastic collisions. These are just few. There are other problems like wave breaking. Some problems involve very large changes in density, for example, star formation. And then there are multi-phase flows like volcanic eruptions. and fragmentation, which involve collision of solid bodies, like for example plane crashes. So far there are many numerical methods available with us that we use to model small and large deformations. Let me take you through those. So before that, I would like to mention that any problem we have in the physical world, it can be explained through mathematical expressions, and then we can devise a set of governing differential equations for that problem. However, the analytical solutions to those differential problems can only be obtained when the domain is homogeneous and when we are dealing with somewhat similar or regular geometries. But if we want to analyze real-life structures which aren't just simple geometries, we need some tools. So numerical method or numerical modeling is one way to do that. Through it, it helps us to transform those differential equations into a set of simple simultaneous equations that can be solved easily. Some of the methods are, let's say, mesh-based or grid-based methods, which include finite element, finite difference methods. So discretization is a very important part of numerical modeling because otherwise we have infinite data points. That means infinite amount of data. So it's important that we discretize the model first. In grid-based or mesh-based methods, the discretization is done using a mesh, and then the domain is discretized into small elements, and it's the nodes where the information is collected, I'd say, or calculated. Then we have hybrid methods like material point method or particle finite element methods, where we have a background mesh as well as particles. So let's say if we need to calculate some properties like mass, velocity, etc., they are calculated at these particle points, material points, and then they are extrapolated onto the background mesh. And talking about mesh-free methods, there is only one truly mesh-free method which is there. Some people call these methods as well mesh-less methods, but if there is one truly mesh-free method, that is SPH, so there is no background mesh, the domain is discretized into particles, and then things are carried out. And then we have Then we have other problems involving, let's say we have a mixture of rock and soil, non-homogeneous materials, like we have jointed or fractured rocks. So these methods like discrete element method or discontinuous deformation analysis, these are used to model that kind of problems. Now all these methods have their own advantages and disadvantages. No method is better than the other. All are suited to different kind of problems. So SPH here, why I'm using SPH in my work so far, or why SPH is in use so much in the geomechanics or the solid mechanics research, is because of its robustness and the ease with which physics can be incorporated into it. Now coming to small particle hydrodynamics or SPH, as I already mentioned, it's a mesh-free method. It's particle-based, and it's based on the Lagrangian approach of continuum. So those who don't know, so basically, if we want to understand fluid flow, there are two approaches that have been proposed. One is the Lagrangian approach, and another is the Eulerian approach, which have been named after the scientists that proposed them. So Lagrangian approach is like, if we have a, let's say, a fluid flowing, we are tracking one particle as it moves from, let's say, this point to this point. We are tracking each particle. It's like, for instance, a woman carrying her dog. She is tracking her movement, her velocity, her position. She can track it at each and every point. So it's like that. So we are following one point as it moves from one point to another in the Lagrangian approach. However, in the Eulerian approach, we have a volume element, let's say. So at any point of time, we are focused on how much fluid or how much continuum is trapped within this volume element. That's the Eulerian approach. So here in SPH, we are using the Lagrangian approach. that the domain is discretized into particles, now we have this central particle here, let's say this one. At any given point of time, it will be surrounded by another set of particles around it, right? So there will be some kind of interaction going on here. See here, I will give you a little example. If you have seen a cycle touring race, has anyone seen a touring cycling race? So in that, the individual cyclists, it's not a race between individual cyclists. Basically, packs of cyclists are moving together, very closely. So there is a pack here, there is a pack here. They are moving forward and they are moving very together. So what happens ki dhakam ki ho rahi hai. So energy is being transferred from one cyclist to another. Velocities pe asar pad raha hai. That's how the interaction between these particles can be understood or visualized. So for any fluid, let's say, the governing equations are these momentum, first one is momentum, continuity and the momentum equations. These are the governing equations for any fluid. Now if we want to find a solution means if we want to determine the properties of the fluid at different points of time, we can do that, we can find the solution, but we have to take care that some fundamental laws aren't broken. We have to take care that the mass is conserved. We have to take care that the momentum is conserved. So these are these two equations which need to be taken care of. So here we have two main unknown variables, primary unknown variables, which is the density here, density and the velocity. These are the primary unknowns, and then we have dependent unknowns, like for example acceleration, we have stress state, we have rate of change of density, we have rate of change of velocity, etc. So we have to calculate all these at different points of time. So what we do is, firstly we can calculate rho and v, then from that we can calculate the rate of change of, let's say density and rate of change of velocity. So the solution strategy for SPH is like it uses explicit integration scheme, which means that if we have these properties, let's say we have at time t, we have the density, velocity, and we have all these parameters known for the fluid. If we are able to calculate all these properties at time t plus delta t, then we should be able to calculate these properties at other time steps as well, meaning this is how the process will continue. So in SPH, so basically some approximations are needed when we are integrating the, let's say we are determining the forces between any two particles at some point. Let's say we are determining the force between this particle and let's say this particle at any point. We need to, so we have two things. We have space and we have time. Firstly, we need to know what is the state of the fluid, what are the forces, what are the masses of different particles, what are the velocities at different time frames. And when we know that when we calculate these properties for different particles, we need to know the overall behavior of the fluid from that. So it needs interpolation. That interpolation is taken care by this kernel approximation, wherein f of x, let's say, is the any field property, any field function, let's say velocity at any position x, and w is the weighting function. So is anyone familiar with the Dirac delta function here? So so it is a function, it is like of this form, let's say minus infinity to infinity, delta x dx is equal to 1. So the integral equals 1. This function, it is such that its value at one point is, it has a very high value at let's say 1 point. At all other points its value is 0. This w here, it is known as the kernel function. It is basically a modification of the delta Dirac function. In the next slide, if you look at it, this is how it varies. This is how it varies. So basically, it's not 0 in all places. Like I mentioned, it's a modification of the Dirac delta function. So it is 0 at the ends of the support domain. Support domain is basically the those close number of particles that the central particle will interact with. Obviously, the fluid domain is so big, or the continuum domain is so big, it will not interact with all other particles. It will only interact with this close niche of particles at given point of time. So, this kernel function varies such that its value is 1 at the center, the particle under consideration, and its value goes on decreasing and is 0 at the end of the support domain. Now, these are the different approximations given for W, and it depends upon Q, which is the ratio of the distance between any two particles at any given point of time, and the H. H is the smoothing kernel or the smoothing length, which basically defines the size of the support domain around the central particle, around any SPH particle. Now, previously, if you remember the previous slide, initially I showed you some of the large deformation problems that we witnessed around us. So, these are the SPH, these are the visuals of how these problems can be solved in SPH. This is one simulation of the Rishi-Ganga terrain wherein the debris flow took place and it destroyed a hydropower plant in its way. And another example that I will show is this is another example of a railway embankment failure due to earthquake. Yes, these are some more examples of how SPH can simulate. This is the example of how fracture is being simulated by SPH. And this is the another example of elastic deformations in the rings which are colliding into each other. And there are other examples, there are many other fields where SPH is being used and has practical application. Like for example, in astrophysics, metal forming, beam oscillations and so on. So I think that's all. These are some of the references if you want to go through. Thank you. So I try to make it as simple as possible, but if anyone is interested in knowing more about it, you can take resources from me. You can come to me anytime. Thank you.
Yes, questions or suggestions regarding presentation, regarding presentation styles, what you liked, what you didn't like, where she might improve. किसी को कुछ समझ आया? Okay.
So thank you so much for listening. Now I request Tajul to come forward for his presentation.
Mic off.
Just one suggestion: if you do not interact, there is no need. Trust me. Try to interact. Or if you want us to leave, we can leave. Who's hesitating to interact with the participants?
I think I don't need this. न्यू
प्रेजेंटेशन फोल्डर
नीचे नीचे फोल्डर है न्यू ऊपर इसमें प्रेजेंटेशन लास्ट में जो है ना हेलो 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 हेलो
Hello.
मी असं
yes. Just check if it is working.
Good evening, everyone. First of all, thank you, Nadim, for introducing the purpose of this lecture to everyone so nicely. So now this is a very short topic which I am going to discuss. I think this most of us, at least once in our research, we use how to select the ground motions. There are actually many techniques you can use, and the conventional methods which everyone uses using the code-based response spectra. You use the target spectra which is given in our code like IS 1893 for 2016. Then you feed the response spectrum as a input in some ground motion database. Then you select the ground motions which is matching that response spectrum. So this is conventionally what we do. Okay, so let's start with the basic steps. Conventionally, what we do first, we have to choose some target spectra. So, for example, you have the target spectra which is given in the codebook IS 1893. Then you go to some ground motion database. For example, we have here ground motion database. It's basically a like a store of lot of ground motion sets which we have experienced in the past in the various parts of the world. Then you provide the input parameters. This I will talk later. What are those input parameters you need to input? And after that you have to insert the target spectra. You have selected the target spectra in the first step. Then you insert the target spectra in the database. Then define the period range for scaling of ground motions. It means if you see the target spectra given in code, it's